Hi everyone, today we're going to be talking about two groups on the periodic table, the post-transition metals and the metalloids. So, today we're going to be learning the properties of the post-transition metals and the properties of the metalloids. We'll also be adding both of these groups in on our periodic table and talking about the charge for ions in column 3A, which includes both some post-transition metals and some metalloids. Before we get started, you're going to need your periodic table, some colored pencils, and notepaper and a pencil for taking notes with. So we're going to start with the post-transition metals. Now the post-transition metals are called this because they are metals and they come after the transition metals. So if the transition metals was this big block in the center, the post-transition metals are just to the right of that. Now you'll notice this is kind of a weird group. It's not as sort of set in a column as many of the other groups we've looked at. It includes aluminum, gallium, indium, tin, thallium, lead, and flerovium. So I want you to take a moment, go ahead and pause this video, color in those 7 elements. Make sure you're looking really carefully at this to be certain that you're getting the right ones, so just those 7. And when you are ready, hit play to resume the video. All right, ready? So before we go on, I want to take a moment and talk about the things in column 3A. So column 3A includes several of these post-transition metals and some things that aren't quite. So nihonium, we can't say for sure if it's a post-transition metal because it's only created in labs. It doesn't exist naturally. So we really haven't had a chance to observe its properties and confirm this. And boron up here is actually going to be in our next group, the metalloids. But this column can form ions. And if you think about column 3A, everything in that column is going to have 3 valence electrons. Remember, you can tell how many valence electrons something has by which column of the periodic table it's in, and you can tell how many shells of electrons something has by which row of the periodic table it's in. So something like aluminum has 3 valence electrons and 3 electron shells, while gallium has 3 valence electrons and 4 electron shells. Now, for everything in column 3A, with those 3 valence electrons, they're going to want to become stable. And everything wants to become stable typically by either filling out their outermost electron shell or emptying it. So there's sort of 2 ways you could do that. You could either gain electrons or you could lose electrons. Now, if you have 3 valence electrons, your options are either get rid of those 3, so that now you have no valence electrons, you've completely emptied that outermost shell, now the next shell in is full, or you could gain a whole bunch of electrons. So with 3 valence electrons, you would either have to gain 5 electrons, or you would have to lose 3. Losing 3 valence electrons is going to be a lot easier. So anything in column 3A, that's boron, aluminum, gallium, indium, thallium, and nihonium, if they form ions, they're going to do so by losing 3 electrons. Now remember, electrons are negative. So if we started out with no charge, a charge of 0, and we lost 3 negative charges, that's sort of like if you had 0 and you subtracted negative 3. Now when you lose a negative charge, it makes you more positive, right? 0 minus negative 3 actually gets you to positive 3. So the charge of ions in column 3A is positive 3. So above your periodic table, you should see plus 1 in the first column, plus 2 in the second column, plus 3 in column 3A, and you should have minus 1 written above column 7A as well. So those are our post-transition metals. Now the first thing to note about the post-transition metals is that they're metals, and like all metals, they're going to share certain properties. They are malleable, which means you can hammer them to different shapes without them breaking. They're ductile, they're conductive, and they always form cations. Now, the thing that makes the post-transition metals special is that they tend to have really low melting points. So if you think back to when we did paper circuits, you used this stuff solder, which was a metal wire, to form a sort of molten glue that you could use to connect your LEDs to your copper tape. Now when you took that soldering iron and you stuck it on the copper tape, it didn't matter how long you held it there, that copper never melted. That's because copper, a transition metal, has a really high melting point. But the solder that you used is made out of tin, or in some cases lead, and both tin and lead are post-transition metals. So like all the post-transition metals, they tend to have really low melting points, low enough that you could melt them with a soldering iron. There are some, like gallium, that can melt at body temperature. So if you hold gallium in the palm of your hand, it'll just melt. Indium is a metal that's so soft you could literally bite it with your teeth and you could break it in half that way. So the post-transition metals tend to have really low melting points, and that is something that we can use. It makes them useful. So we're going to take a moment and show you, this is gallium being poured into somebody's hand. So here they've just taken a bottle containing some gallium and they've stuck it in warm water just from a tap. And this gets it hot enough to melt the gallium. And then you can just pour it directly into your hand. Gallium is non-toxic, and it's a very weird experience because it's quite dense. So it feels pretty heavy, but it looks almost like a water droplet. You can see it beads up. It's got a lot of surface tension, and it will stay completely liquid at room temperature. If you freeze it, it'll turn right into a solid again. So that is gallium, which is one of our post-transition metals, and it really shows off that low melting point. So next we're going to talk about the metalloids. The metalloids are a really weird group. The thing to know about the metalloids is that there's some disagreement about exactly where to draw the line between the post-transition metals and the metalloids. So think of it almost as a spectrum. If you are all the way over in the transition metals, you are like really, really metally, like you've got the metal properties really well. When you move into the post-transition metals, you start acting a little bit less like a metal, right? We've got that sort of bizarrely low melting point for the post-transition metals. When you move to the metalloids, in some ways they act like metals, but in other ways they act like nonmetals. So the metalloids contains boron, silicon, germanium, arsenic, antimony, tellurium, astatine, and tennessine. So I want you to go ahead and fill in boron, silicon, germanium, arsenic, antimony, and tellurium on your periodic table. You're going to go ahead and shade those in, and make sure that once you've done that, you add them to your key. You will notice that I didn't stick this under metals or nonmetals because metalloids aren't really either. They're sort of in between those two. So go ahead and fill in those 6 elements on your periodic table and make sure that you label them as metalloids on your key. Pause this video and then unpause it when you're ready to move on. All right, ready? So, when you hear the phrase metalloid, in your head you should translate that to metal-ish. These are sort of metals, and they're also sort of nonmetals. So if you think about our metal properties, things like being conductive, metals are conductive. They've got that nice electron sea where they can easily trade electrons back and forth. Nonmetals tend to be insulators, which means they don't conduct electricity or heat well. The metalloids are right in between. So while the metals are great conductors, the nonmetals are terrible conductors, the metalloids are in between. So they sort of conduct. And that property of sort of conducting can actually be really useful. For this reason, we use these in a lot of computers. So many computer chips will be made out of silicon, which is one of these metalloids. Now, while metals are malleable, metalloids tend to be brittle. That makes them a little bit more like the nonmetals. Imagine you've got two containers of soda. One is an aluminum can, and one of them is a glass bottle. Now, the glass bottle is made of silicon, which is a metalloid, while the aluminum can is made of aluminum, which is a post-transition metal. Imagine the difference between stomping on those two different containers. If you stomp on an aluminum can, it's just going to crush, right? It's malleable, right? You can hammer it or squish it into a different shape. If you stomp on a glass bottle, it's going to shatter because silicon is very brittle. That's much more similar to the nonmetals. In terms of how they react, they're really in between. So metals can do this thing called forming alloys. So if you melt down a bunch of, say, iron and copper, and you mix it together, you can create a new metal out of that. So those are called alloys. So things like brass and bronze are examples of alloys of metals. You won't find them on the periodic table, but they are made out of elements on the periodic table. So you can form alloys with the metalloids, but they can also form covalent bonds, which is something you normally only see with the non-metals. So most metals can't form covalent bonds, but the metalloids can. So the metalloids, they're sort of like metals, they're sort of like non-metals. Really, they're the in-between group. They're the boundary, the border between things that are metals and things that are non-metals.